All right, so today I'd like to continue our discussion of surface integrals, but this time I would like to do it for functions as opposed to simply parametric surfaces. So what do I mean by this? I mean, instead of looking at some UV parameterization, I want to look at an actual function and determine some sort of flux going through that function, given by usually something elementary, because we don't want to make the integrals too hairy that we let you guys use Wolfram Alpha. But anyways, we'll look at some surface integrals for functions today. Why don't we get started by looking at the definition, or really the derivation of the idea here. It's going to be very similar to what we did in the last kind of set of videos, where we determined that the double integral would be sufficient given some square root factor of involving the partial derivatives plus 1, and then if we squared that, we would get the proper thing. So what we will do is we'll let g equal some x and y. So our parameters for this are actually going to be x and y. So that would make sense. So if I have an x parameter and a y parameter, I pick any point on a domain governed by x and y, and it beams me up to some z parameters. So z can be fully dependent on x and y. What is this actually? This is just a trivial two-variable function, a multivariable function that we've been dealing with for a while. So we're defining this in the terms of a multivariable function. So what do we need to do to find the mixed partial derivatives? Well, if r is defined as kind of the vector function of these parametric equations, then r sub x will be e sub x, so you take the derivative of x, it's 1, plus the partial derivative of x with respect to g times the e sub z basis vector. That should be the z basis vector, not the x basis vector. And then r sub y will be e sub y plus the partial y of g e sub z. Okay, so now what we want to do is we want to find its cross product of these two vectors and then plug it into a magnitude formula. And what we get is we get partial x z squared plus partial y z squared plus 1. Now this should not be anything new. This is something we derived a couple videos ago. So that's why I didn't go through the whole the cross product hamana. So what we really do in the end here is we can define this whole formula in terms of a surface integral now, because we know that the surface integral is equal to the integral over a domain of the function in terms of the parameterization times the surface area element, which is that partial squared plus 1 with respect to the differential area. Okay, so now we have a proper definition. Now what's interesting is this could alternatively work if, say, instead of g of x and y, instead of z equals g of x, and instead of doing x equals x, y equals y, and z equals g of x and y, you could do x equals x, y equals h of x and z equals z. So you really do it in any sort of orientation that you like. You can also do it in polar coordinates, spherical coordinates, whatever type of double cylindrical coordinates, whatever type of coordinate you want. So let's try an example to sort of demystify this. And again, I warned you this will get technical. So let's find the surface integral over z ds, and we're given a piecewise surface. Okay, so we haven't really been dealing with piecewise surfaces recently, but never too late to start. So let's draw this out. As always, that will be helpful for us. So there is our badly drawn coordinate grid. I am not an artist, did not go to art school, but maybe it should be a thing that math students should go to art school so that they can visualize what they're doing a little bit better. Anyways, what we're given the first surface, and this is given by the unit cylinder, so we can draw like a cylinder in here, and the second surface is x squared plus y squared is greater than or equal to 1, or less than or equal to 1. So that's the second surface. So what the second surface actually is. And then the final third surface is equal to z equals 1 plus x. So z equals 1 plus x is going to be a graph that takes in any y value, or y is independent, it's a plane. So z equals 1 plus x is, if we label this as our x-axis, then we go up to 1, and then it's kind of a plane that kind of intersects downwards like that a bit. Oh, shoot. All right. Anyways, whoopsies. What we're going to be getting is we're going to be getting kind of a, not like I drew this too small, but it's going to be like a cylinder looking thing, but the top is going to be at a slant. So I don't really know what that looks like. A skyscraper maybe, if you draw it like that, or like a cylinder that someone's cut in a random angle. How about a cucumber that someone's cut in a random angle? Maybe that's what we're looking at. But anyways, we're given these three surfaces. This is surface number 1. This is surface number 3, and then surface number 2 is down here, surface number 2. Okay, so anyways, let's try to determine this. So we have a cylinder, we have a cylindrical shape. So if we have a cylindrical shape, then that means that we're going to want to use a cylindrical coordinate system. So let x equal to cosine theta, we're going to use polar coordinates for the bottom, and then we use z as our normal vertical component. So we get x equals cosine theta, y equals sine theta, z equals z. Theta goes between 0 and 2 pi, and z, we're going from 0, and then we're stopping at 1 plus x, and 1 plus x in the polar coordinates, x is cosine theta, so we get 1 plus cosine of theta, so we're between 0 and 1 plus cosine of theta. Now if I want to find the cross product to find this magnitude, take r sub theta and cross it with r sub z, so we plug it into the determinant formula, so e sub x, e sub y, e sub z, take the partial derivatives of r sub theta, so we get negative sine theta, cosine theta, and 0. And for the other guy, we take the derivative with respect to z, we get 0, 0, 1. So then that yields cosine theta e sub x plus sine theta e sub y. Okay, so we have a proper differential element here. Now if I take its magnitude, cosine theta squared plus sine theta squared is equal to 1. Free mill. So now what we're going to do is we're going to evaluate each of these surface integrals independently. So the first surface integral is along the side. So if we take the surface integral along the side, we get the integral between 0 and 2 pi, then the integral between 0 and 1 plus cosine of theta of z dz d theta. This is an integral we can do well, but then we end up with the integral between 0 and 2 pi, 1/2, 1 plus cosine theta squared d theta. And this you FOIL out, then you do the double angle substitution, and then you can get 3 pi over 2. I'm not going to go through all that because we should know how that works, right? Well, then we also have the integral over z for the second surface, but this one's trivially 0. And then finally, we have the integral over the third surface. Now this one's a little bit more complicated, but we're going along the bottom surface, and this is given by we're going over the top surface, the one that cuts off the thing. So the function, this is where we're going to use the definition that we found in the last slide, whereas we use the parameterization for the function, right? So we use the integral between 0 and 2 pi, integral between 0 and 1, 1 plus r cosine theta. Then we have that square root of 2 from the partial derivative squarey thing for the in the arc length formula. You get square root 2 r d theta, because we're using polar coordinates, we plug in that extra r. So you get the square root of 2 integral from 0 to 2 pi, integral from 0 to 1, r plus r squared cosine theta, d theta. And then this becomes 2 times the square root 2 times pi. And then if we want to find the total flux, if you will, or the total surface integral, we add up all of the surface integrals that we found. First one, and the second one 0, and then the third one. So we get 3 pi over 2 plus 2 root pi. No need to simplify that. You can just neglect the 0, but you don't want to add a radical to a fraction. That's a messy business. Anyways, thanks for watching today's video. In the next video, what we want to do is we want to look at vector fields. So this is really going to be important. So like say you have a plate or something, you expose it to an electric field, what is going to happen with that electric field? So we'll look at that, and then we'll look at some applications, then we'll look at the fundamental theorems of the curls and divergences. Thanks for watching. We'll see you in the next video. Bye.